Hi, good evening. So today we are starting momentum. You can write the topic momentum in bold letters. Yeah. So write down the topic momentum. Okay. So and then you can write what is momentum. We know momentum means uh, the mass times velocity of a particle. If let's say for example a ball. A ball has a mass and a velocity. If it has a velocity, it has momentum, right? If it stops, the momentum is zero. If the ball is stationary, its momentum is zero. Okay, right. So we can write it is the product of an object's mass and its velocity, represented as P equals mv. So momentum is given by P equals mv, and here you can find the letter P and V are bold because momentum is a vector quantity and velocity is also a vector quantity, right? So, but the mass is a scalar, right? So, therefore, the momentum is a vector quantity. So, here momentum is given by the mass times velocity. So, we can write P equals mass times velocity. So, here you can find that velocity is a vector multiplied by a scalar. In vectors lesson, we studied that if we multiply a vector by a scalar, let's say now this mass is obviously greater than zero, no? So we are multiplying by a positive scalar. Therefore, we obtain a new vector which is pointing in the same direction, right? So therefore, the direction of the uh, momentum is in the direction of velocity. Okay, so after writing this, you can write the momentum is a vector quantity. Momentum is a vector quantity. And its direction is in the direction of velocity. Its direction is in the direction of velocity. In the direction of the velocity. Okay. So the momentum is defined by mass times velocity of a particle, of an object. Okay. And then momentum is a vector quantity and its direction is given by the direction of the velocity. Okay, you can raise your hand once you're done writing up to here. Okay. No other notes before this. So we are starting from momentum. So straight away we can start with the definition. The momentum is defined by the mass times velocity of an object. Okay. So if you finish, you can start this question. Mass of a car is 2,500 kilogram. It's moving with the velocity of 25 meters per second. Find its momentum. And sorry guys, last Tuesday also I couldn't have the class because there was a rain continuously. The whole day it was raining, so the connection issue also there. And moreover, the main reason is I was sick, actually cold, since last Saturday. Today morning only, alhamdulillah, I got recovered. So yeah, that's the reason I couldn't do. But the way, if possible, no, definitely either Saturday or Sunday, I will do a cover up session. I will let you know by Saturday. No, I'll let you know by Saturday morning. Yeah. Okay, then so you can do this question. A mass of a car is 2,500 kilogram and it is moving with a velocity of 25 meters per second. Find its momentum. If anyone done, you can drop your answers in the chat box. Okay, I got a couple of answers. Okay, both same value. So therefore the answer might be correct, yeah. So here simply we can find the momentum by taking the mass times velocity in V. So the mass is 2,500 kilogram, 2,500 kilogram, and the velocity is 25 meters per second. So 25 into 25 is 625, and then followed by two zeros, kg ms minus 1. Okay, so by the way, here we want to try the unit of momentum. Unit is kg ms minus 1, kilogram meter per second, or else we can use another unit, Newton second. Okay, so these are SI units, kg ms minus 1 or Newton seconds. Okay. Okay, write down the next question. Question number 2. Mass of a ball is mass of a ball is 400 grams and it's moving with the speed of, with the velocity of, let's say 18 kilometer per hour. What is the momentum of the ball? What is the momentum of the ball? Okay, quickly do this. Don't take much time because today we have to finish the momentum completely. Okay, I got an answer from a student. Okay, two answers and both are same value, so I think the answer might be correct. Okay, so here first you have to write this in SI units, right? So P equals mass is 400 grams, so in kilogram 0.4, and speed is 18 kilometer per hour. That one we want to convert into meters per second. We know kilometer per hour. To convert into meters per second, we have to multiply by 5 over 18 meters per second. So 18 and 18 cancel, we get 5 meters per second. So we get here 5 So therefore, it will be 2 kg ms minus 1. Okay, good. So the momentum is 2 kilogram meter per second. Okay. Okay. So write down the topic, the principle of conservation of momentum or linear momentum conservation principle. Write down the topic, linear momentum conservation principle. The principle of conservation of linear momentum. Okay. So it says the total linear momentum of an object or a system. The total linear momentum of an object or system remains constant in a particular direction if no external force is applied in that direction. Okay. So first you can write down the principle and then I will explain you. Raise your hand if you finish writing. Okay. So I'll explain you. So it says the total linear momentum of an object or a system remains constant in a particular direction if uh, no external force applied in that direction. So I will explain. So let's say I have an object. Okay. So I take this. Okay. I placed it on my hand. Okay. Now apparently it remains at rest. Okay. So now uh, now this is at rest, which means the momentum is constant. The constant value is 0, right? Because 0 is a value, right? Okay, so it's a constant value, so it remains 0. Okay, this is not moving in this direction because there is no any unbalanced external force acting in this direction. In the horizontal direction, there is no any unbalanced external force acting on this. But if you consider the vertical direction, obviously it experiences a unbalanced force. Sorry, experiences a external force, right? We know the gravitation attraction always acts on an object vertically downward, but it is balanced by the normal reaction force, right? So therefore, you can see the momentum is not changing; it remains constant. But if I suddenly take my hand, what happens? If I suddenly take my hand, it will drop. Why? It will accelerate vertically downward because there will be a, so when it's falling downwards because of the earth's gravitation attraction. So when I take my hand there, then no longer normal reaction force will be there. So there will be an unbalanced force in the downward direction. So this will accelerate downward. So when it's accelerate downward, so it's falls like vertical, right? It falls in a straight line vertically downward. So there is no any movement in the horizontal direction because there is no any external force in the horizontal direction. So while this is moving, while this is falling downward, The momentum in the horizontal direction remains constant. Okay. Is that clear, everyone? Is it clear? I need a response from each and everyone. So the momentum conservation is directional. Okay. Zufar, Abhiushani, please give me a response whether you understood or not. Okay, good. Atika, did you understand? Okay, good. Okay. So I hope you wrote this definition or the principle. So then now I can write here. We know according to Newton's second law, according to the Newton's second law, uh, according to Newton's second law, the force is proportional to the rate of change of momentum. In fact, it is equals to the rate of change of momentum. Okay. According to Newton's second law, force is proportional to rate of change of momentum. Okay. And the direction of the force is in the direction of change in momentum. Now, in your O levels and all, you may have studied that Newton's second law is equals to F equals ma. That is true, but it's only a specific condition. You can use this equation F equals ma only if the mass is constant. Okay, so this is only a special case when the mass is constant. But the actual definition, I mean, if you study the Principia Mathematica, that book written by Newton, in that book it has stated as the external force acting on an object is directly proportional to the rate of change of momentum. He didn't mention like force is equals to mass times acceleration as the Newton's second law as the definition, but later on we can get that also as a special case. Okay. So we know according to Newton's second law, so I can write according to Newton's second law, force is equals to the rate of change of momentum, delta P over delta T, right? Then I can say if F equals 0, if the external unbalanced force is equals to 0, now even if F equals ma, here you write the net force, no? Net force. Okay, so therefore this is also the net force acting on the object. Net force. If the net force is 0, then according to this equation, delta P over delta T, we have this is equals to 0. Okay, so then I can write if delta P over delta T equals 0, then straight away we can write delta P equals 0. So the change in momentum is 0, right? Change in momentum is 0. So change in momentum, how do we find for anything? Like if you want to find a change, for example, a change in velocity, how do we find? We take the final velocity minus initial velocity. So likewise, then change in momentum, we can write final momentum Pf minus Pi is equals to 0. So therefore, you take this to the other side, Pf equals to Pi. So therefore, the final momentum of the object or system is equals to the initial momentum. You can write down this. Okay. So this is the momentum conservation principle. Okay, it says if the momentum is if the unbalanced force is zero in a particular direction, then the momentum remains constant in that direction. Okay, the total linear momentum of an object or system remains constant in a particular direction if no external unbalanced force is applied in that direction. Okay, you can't, if you write this entire thing without this unbalanced word, then it's wrong, no? Because now you can see if I take this object, it experiences unbalanced force. Sorry, it experiences external force, which is gravitation acceleration acting on this by the earth, and also the normal reaction force acting on this by my hand. So those two are external forces, right? But the main thing should be satisfied is there should be an unbalanced force. Okay. So if there is no any unbalanced force acting on an object in a particular direction, then momentum will be conserved. If the momentum is conserved, means change in momentum will be zero. So therefore, final momentum is equals to the initial momentum of the object or system, whatever the thing that we are considering. Okay, so if you finish writing this, you can raise your hand. Okay, if anyone's still writing, you can take a screenshot. 3, 2, 1. Okay, so let's straight away move on to a question. Okay, so here the example. So this one I'll do. A block of mass 2 kilogram is moving with a velocity of 3 meters per second. 3 meters per second toward another block of mass 1 kilogram, which is at rest, and they both collide. Okay. After the collision, the blocks stick together. Find their common velocity after the collision. Okay. So let's say there are two blocks. Okay. So here, a block of mass 2 kilogram. So this is 2 kilogram is moving with a velocity of 3 meters per second. So the velocity is 3 meters per second towards another block of mass 1 kilogram. Right, kilogram per kilogram, which is at rest. So which is at rest means it's not moving, it's stationary. So the velocity is zero. Initial velocity is zero. Okay, right. So this is, we can say, before moments before collision. Before collision. Okay, before collision. And this is after collision. So the mass 2 kilogram and this is 1 kilogram. And it says after the collision, the blocks stick together, right? Okay, so after the collision, they stick and move. So 1 kilogram, and it move with a common velocity, let's say v. Okay, so this is after collision. After the collision. Okay. Okay, so before moments before collision, 2 kilogram is moving with this direction 3 meters per second, and it's collide with this 1 kilogram, and then they stick and move. Okay. Okay, so now we want to find the velocity, this v. For that we have to use the moment linear momentum conservation principle. Okay. Okay, so here I will consider one more thing. Here this one is the mass, the blocks 2 kilogram and 1 kilogram at the moment of collision. Okay, 1 kilogram, so 2 kilogram, 1 kilogram. Okay, so this is at the collision, at the moment of collision. Okay, now we know, it's our simple instinct that if two objects collide, or now your friend is sitting in your class room, just stationary, just if you go and punch on his face, definitely he will feel a force, no? If your hand collide with your friend's face, okay, so there will be a force, right? So here, this is the force at the collision, let's say F. Okay. Okay, so then according to Newton's third law, there will be equal and opposite reaction force. Okay, F. Okay. Okay, now I will ask you a small question. Okay, I'll ask you all a small question. Can we apply linear momentum conservation principle to the 2 kilogram mass? Okay, listen carefully. Can we apply linear momentum conservation principle to the 2 kilogram mass? Okay, let me know yes or no in the chat box. Also, I need an explanation. I would really appreciate if anyone who can turn up the mic and give me the explanation. I would really happy. It would make my day, honestly, I'm speaking. By the way, I need a response from each and everyone, yes or no in the chat box. Okay, that is mandatory. And again, I would appreciate if anyone can turn the mic on and let me know the reason. If your answer is yes, you have to explain why yes. If your answer is no, you have to explain why it is no. Okay. Come on, guys, it won't take to text 2 3 letters, right? Yes or no? It has either 3 letters or 2 letters, right? Don't take at least 30 seconds. There are 6 students in this class now. Okay, I get mixed answers. I'll repeat the question again. Can we apply linear momentum conservation principle for 2 kilogram mass? 2 kilogram mass. Please, each and everyone should respond. If you know the answer, you can say yes or no. Otherwise, even say don't know, but rather don't be stay silent. It will make me really difficult. To, yeah. Now, to answer this question, you have to understand the linear momentum conservation principle. What it says, the linear momentum of an object remain or system remains constant if no external force is applied on it in that particular direction. Okay, so I will explain. No, it is not equivalent to Newton's second law. So Newton's first law, but again, no external force applied means, yeah, sort of, yeah, like that only. Yes. Okay, the answer is the question I asked you. Okay, first I'll read the question again. Can we apply linear momentum conservation principle for 2 kilogram mass? The answer is no. Okay, the reason, because if you consider this 2 kilogram mass, during the collision there is a external force acting on it, right? There is external force. If you study the principle properly, then you will say that no, because here you can see at the moment of collision there is an external force acting on this 2 kilogram mass, right? Okay, again I'll ask another question. Can we apply linear momentum conservation principle for this 1 kilogram mass? Can we apply for this mass? Come on, this time I need, I'm expecting answers from you with pata pata taggal and answers. I got only one answer. Others, please respond. Okay, I got two answers. What about other four? Yeah, Hiroshi, you are correct. So that's what I'm going to explain. Yeah. Okay, so the answer is again no. We can't apply linear momentum conservation for this 1 kilogram also, because it is also experiences an unbalanced force in uh, horizontally to the right. Okay, but if I consider this system, so now if I consider this system, there is no any external force acting in the horizontal direction. I mean unbalanced force. Because now here this F and this F cancel each other. It is actually an internal force. It's a it's only an internal force to the system. Right? If you consider the system, there is no any external force acting on the system in horizontal direction. Therefore, we can apply to the system. Okay. Okay. So uh, let's write down. I will give you a note. First, you can draw this. Okay. Before collision, and then at the moment of collision, and then after the collision. Now in doing questions, when you are doing questions, this one is not necessary. Okay, this at the moment of collision I drew here because for the purpose of explanation, but in questions now we have other examples also. After this question we have more questions, then we will, you have to consider only before the collision and after the collision. Okay, and no need to draw uh, the at the moment of collision. If in case in a question they ask, then you have to draw like this only. Okay. Okay, then you can draw this, and then I will give you the note, a small note, and then after we will find the velocity. Quickly draw. Don't, no need to keep rule and draw this. Okay, you can just bare hand draw this. Okay, so you can write the first point. Here we can't apply linear momentum conservation principle to the 2 kilogram mass, because here we can't apply linear momentum conservation principle to the 2 kilogram mass, because it experiences a external force horizontally to the left at the moment of collision. Here we can't use linear momentum conservation principle for 2 kilogram mass, because it experiences an external unbalanced force uh, in the horizontal direction. Okay, so here we can't use linear momentum conservation principle for 2 kilogram mass because it experiences an horizontal external force in horizontally to the left at the moment of collision. So likewise, the second point also you can write for the 1 kilogram mass. Okay. So for 1 kilogram mass also we can't use the linear momentum conservation principle, but we can use linear momentum conservation principle for the system. Okay. So the third point you can write, we can use linear momentum conservation principle. We can use linear momentum conservation principle to the system because it does not experience any external force. It does not experience any unbalanced external force in horizontal direction. Because it does not experience any external unbalanced force in the horizontal direction. Okay. So I think it is clear. So let's now find the value of V. So then we can write using linear So first I can write since no external unbalance force is applied on the system, since no external unbalance force is applied on the system in horizontal direction, we can use linear momentum conservation principle. So using linear momentum conservation principle to the system. So we are applying to the system. So when you are solving a problem using the linear momentum conservation principle, this one is must. You have to write this. Okay, must. You should write that. Okay. For that also writing one point is there. Okay, so you can write instead of writing this entire thing, you can say since F equals 0 or no external force is applied. Okay, something like that you can write. Okay, so using linear momentum conservation principle. So total momentum before collision is equals to total momentum before collision is equals to total momentum after the collision. Okay, so another important thing that momentum is a vector quantity, right? So it has a direction. Since momentum is a vector quantity, it has a direction. Now, you may have studied in kinematics that when we are writing equations of motion, we have to consider a particular direction, right? When we are finding the resultant force, also we have to consider a particular direction. right? So here momentum is also a vector quantity, therefore you have to consider a direction. So I consider this direction horizontally to the right. Okay, so total momentum before collision. So total momentum before collision, we have this mass 2 kilogram. So 2 kilogram is moving with the speed of 3 meters per second, plus the momentum of 1 kilogram. So 1 kilogram into velocity is 0 is equals to the total momentum after the collision. The total momentum after collision, so both the masses stick together and move. So therefore the total mass is 2 plus 1 kilogram and moves with the velocity v. Okay, so then we can solve this. So v equals to here 2 into 3 is 6 plus 0 divided by the multiplication goes to a side, division 3. So v equals 2 meter per second. Okay, so that is very simple. The momentum conservation is very simple. uh, you have to consider the total momentum before the collision, total momentum after the collision. You have to equate that if no any external force is applied on that direction. Okay, right. So quickly write down. If there's anything you didn't understand, you may ask now. Raise your hand if you finish writing. Okay. ලියලා ඉවරනා නම් hand raise කරන්න. Okay. Okay, so this question you have to do. I'll give you only maximum 2 minutes. It's 9:56 now. Quickly do this question. Let's see who finish this question first. Okay, I got an answer. So 2 meters per second. Okay, let's see using conservation of linear momentum. So total momentum before collision BC. So you had to write the full form, okay? So total momentum after collision. Okay. So total momentum before collision, we have a trolley of mass 2 kilogram moving with a velocity of 5 plus another trolley mass 0 gram which is at rest, so 0. And then after the collision, the trolleys stick together, find their common velocity after the collision. So then they will have a total mass of 2 and 3, 5, 2 plus 3 into V. So V equals 10 divided by 5 equals to 2 meters per second. Okay. So therefore the velocity is 2 meters per second. Okay, thing happy. Then we'll move on to the next question. Okay, so here the similar question you have to do it in algebraically. So the mass m1 and the velocity v to another block of mass m2 which is at rest. After the collision, the block sticks together. Find their common velocity. The collision. Okay, if you do it correctly, you will get that common velocity. Let's say W. That will be m1 over m1 plus m2 times v. So you will get this expression for the common velocity. So we can write total momentum before collision using linear momentum conservation principle. Using linear momentum conservation principle, total momentum before collision equals to total momentum after collision. So here mass m1 moves with the speed velocity, the other one is at rest. Okay, here you had to consider direction, and then they will stick together and move m1 plus m2 times common velocity w. Therefore, w equals m1v over m1 plus m2. Yeah, so you can write initial momentum of the system is equals to the final momentum of the system. The same thing. Actually, I have written this. Okay, I have written this. Actually, we know if no applied force, if no external force is applied, the final momentum is equals to initial momentum. So the final momentum is because this is the final momentum, total momentum. Sorry, this is the final momentum, the total momentum after the collision, and this is the initial momentum, total momentum before the collision, the system. Okay, right. So therefore, here you get the common velocity m1 times c over m1 plus m2. Okay, so here it will be clear that the common velocity will be in the direction of initial velocity, because here the other term is uh, scalar. M1 divided by m1 plus m2 is a scalar, so their final momentum is final velocities in the common velocities in the direction of the velocity of the first particle. Now that is obvious. Now if object comes and uh, hit to collide with another object, and it's, can it go backward direction? No. After the collision, it will go in this direction only, right? Okay. 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 So this question also similar to the previous questions. Quickly do this. We will discuss those kind of questions also. No, if after the collision, if the two objects are stick together means, if they stick together means, then they can't go backward. It only go move forward, right? Uh, in other case, if they collide, then if they didn't stick together, then it is possible the one which came in this direction after the collision, it can go in the backward reverse direction. Did anyone get the answer? Okay, so here also we can consider the linear momentum conservation for the system. Okay, so okay, I think Abhushan got the correct answer. Okay, so here total momentum we had right using linear momentum conservation principle. Using linear momentum conservation principle, so total momentum before collision. Okay, or can say the total final momentum. Total final momentum is equals to total initial momentum. Okay. So the total final momentum, so this one has mass 5 kilogram, and then the bullet has mass of, so I write the units later, units 0.02.
என்னடா ப்ரமோஷன் நீ படிக்கணும் நீ ரெக்கார்டிங் உனக்கு மனதுக்கோ தெரியாது மனது കഴിക്കും உனக்கு ஒரு எப்படி
Okay, so here, and then let's say it's move with the common velocity v. So the total initial momentum is mass 0.02 times 300 plus 0. This one initially at rest. So v equals to 0.02 into 300 is 6 divided by, so this actually we can write 5 plus 0.02 is 5.02. That is approximately, okay, so I take 5.02. So this will be approximately equal to, it's dividing 6 by 5. If it divide 6 by 5, you will get 1.2. So 1.2 meters per second. Okay. So actually, if you divide this value, it will, you take 1.19 meters per second. Okay. So in exams, you can do these approximations. That's totally fine, because there you can see there is no much different. Only the difference is by 0.01 decimal. So in this second decimal place, right? So in exam now you have 6, you have to divide by 5.02. So it will take time, no? So in MCQs, you have to take the approximation, like, so 6 divided by 5, so it will be, so it's something like 60 divided by 5, no, so 12, so 1 decimal place, 1.2 meters per second, right? Okay, and let's move on to the next question. Okay, so here this is the linear momentum conservation principle written in another form. The total linear momentum of a closed system of interacting particles or objects or systems remains constant provided no external forces act on the system. Okay. So here I just wanted, I gave this because I wanted to emphasize the meaning of a closed system. Because if in case you got a question like what is a closed system means, if you got a question in paper, what is a closed system, then you should be able to answer it, right? So a closed system is a system where no external forces like friction, gravity are acting. Forces are only internal within the system. Now, if we consider our first example, right, when two blocks collide, So we can't take the blocks, each block as a closed system, because it experiences unbalanced force, right? But if you take the whole thing, both the masses, so it is a closed system only in the, if you take the both blocks as a system, then it is a closed system only in the horizontal direction, but it is not a closed system in the vertical direction, because the gravitational attraction will be there downward. Okay, if it's on a surface, then normal reaction force is also there, right? So a closed system like a space ship in space, a shutter in space, when the engine is turned off. Okay, so it experiences no gravity or anything, so it will be a closed system. Okay, right. Okay, so you can quickly write down this, or you can take a screenshot. Quickly write down. You can take a screenshot and write. Okay, so I'll quickly move on to the next question. Okay, so this next question, it's a explosion. Okay, a stationary bomb of mass 10 kilogram explodes into two fragments. One fragment of mass 4 kilogram moves with a velocity 10 meters per second to the right. Find the velocity of the other. Okay, I'll give you a couple of minutes to try this question. Physics subject is very easy if you understand the concept, the underlying concept, then you can answer to any question just using that basic principle. So here you have to use the linear momentum conservation before the explosion and after the explosion, because now the bomb explodes due to the internal reactions, not the, let's say there is a chemical, for example, you can take atomic bomb or anything, or we take what is the material uh, to make bomb, and potassium, or phosphorus, something like that, I think. Okay, so let's say what we have, it triggers that, then there will be chemical reactions. All the chemical reactions happens very short time. So we know in chemical reactions there are two types, endothermic and exothermic. So exothermic means they release heat out, endothermic means they absorb heat. So there will be a exothermic reaction, so it will be a very fast reaction. So heat, large energy is released in very short time, so it becomes an explosion. So there will be forces within the particles, but if you consider the bomb inside, it will all are internal force pairs, because every action has equal and opposite reaction. So there is no any external force. So a bomb explosion is also but if you trigger by like, let's say there is a bomb when you hit large force like a missile, uh, If a missile hits a strike land, it will explode. So in such kind of explosion, there is a definitely external force. But a stationary bomb is exploding means it is we can consider the momentum conservation. For example, hand bomb. You throw, it falls and falls and it stops. No, after that it will explode, right? Even no need to throw. If you the hand bomb, if you have it, there is a ring. If you pull the ring, it triggers a chemical. So it and then there is a small of the negatina, but for the period. So it will burn and it goes to the chemical and then it will explode. Okay. Anyway, so did anyone got the answer? The velocity of the other fragment? Okay. 40 divided by 6 meters per second. Let's see. Okay. So here, let's say this is the bomb, stationary. So before explosion. And then after the explosion, it divided into two fragments. It explodes into two pieces. So this one is 4 kilogram, moves with velocity of 10 meters per second to the right. Okay, so it's moving to the right. So it is 4 kilogram moves to the right with the speed of 10 meters per second. And then the other piece, the other fragment, has mass of 6 kilogram. So it has some speed v. So we can use since f equals 0, you can apply linear momentum conservation principle. Okay. So initially the total momentum is 0. Okay. Total momentum is 0 because mass time no velocity. So the momentum value is 0. Okay. So here I told you momentum is a vector quantity, therefore you need to consider direction. So I consider to the right. Okay. Momentum is vector, you have to consider a direction. So I consider the right side. Okay. So if we consider this one, it has mass of 6 and then it moves in the direction to the left. I'm considering right side, but it's moving to the left. Okay. So therefore it is minus plus this one 4 into 10. So its momentum in the same direction of that we have considered. Okay. So then here plus into minus 6v we can take to the other side. So it's 6v equals to 40. Therefore v equals 40 divided by 6. So 40 divided by 6, how can we take it? So that is 220, 2 divided by 3 into 10. 2 divided by 3 is 0.66. So into 10 means 6.67 meters per second. It is actually 6.666. You have to round up. So 6.67 meters per second. Okay. If anyone has any question, you can ask. Always remember, momentum is a vector quantity. You have to consider a particular direction. Okay. So I consider to the right side. I consider momentums are positive. So and then the opposite directions are negative. Okay. Okay, let's move on to the next question. Okay. Recoil velocity. So this is also similar to explosions. Okay. So what is the meaning of recoil? Recoil means when you when you shoot, right? When a bullet moves, the gun will recoil back, right? It will move little back. So that is we call recoil. Okay, recoil of the gun. Okay, so here a rifle of mass 4 kilogram fires a bullet of mass 0.05 kilogram with a velocity of 400 meters per second. What is the recoil velocity of the rifle? Okay. You can start this question. That is according to Newton's third law. Every action has equal and opposite reaction. Okay. So when there is a like a spring kind of thing, it's faster. So therefore, equal and opposite reaction force will be there uh, according to Newton's third law. So the uh, total initial momentum is equals to total final momentum. So then we can write the initial momentum is 0 is equals to final momentum. So I consider this direction. The bullet goes to the right, 0.05 into 400 plus the gun. Mass of the gun is 4 kilogram. 4 into v. I assume that you don't know the direction of the velocity. Okay, assume you don't know what will happen. You haven't seen a gun firing, so you haven't seen that gun recoils back. Let's assume that. Okay, So here you don't know the direction of the velocity. So we have using this equation this direction. So you consider using this direction v. Take plus v here. Okay. So then here we get if you take this to the other side, you get minus 4v equals 5 into 400 is 20. So therefore v equals minus 5 meters per second. So here you get minus, which means the velocity is not in this direction, it will be in the opposite direction. Okay. So it will be in this direction 5 meters per second. So therefore recoil velocity is to the left 5 meters per second. I mean the backwards. Okay. 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 So two objects colliding at an angle.